Welcome to EMEE6002. This session is about photovoltaic solar power. So last time we talked about how to convert solar energies into heat energy directly through the solar thermal system. But electric energy is probably the best form of energy in the world because we can transmit electric energies easily, store it in the battery, or be used by all different kinds of electrical appliances. So we make use of a semiconductor to convert the kinetic energy of the photon hit from the sun on the panel to electric energy. So when the sun photon hits on the solar panel, the photon energy will then energize the electrons in this semiconductor. So just like playing snooker, when the white ball hits on the red ball, then the red ball will then move away. So likewise, the sun energy photon hit on this semiconductor, then it will energize the electrons, and electrons can move from the N type to P type, and then the current will be continued. So this is the way how a solar panel can generate current, because the electron inside this semiconductor is energized by the solar light photon. And there are different types of solar panel. For monocrystallized silicons, the efficiency is talking about 70%. For multicrystallines, the efficiency is even lower, talking about 12 to 16%. There are some other solar panels where the efficiency is even lower, talking about 4 to 10% or 9 to 12%. Okay, and nowadays this is not commonly used. And there are some transparent PV panels which are suitable for the installation in the window or in the rooftop, so that sunlight can still pass through and luminize the room, at the same time also capture electricity. And there are some flexible modules that you can bend the PV module. And in Hong Kong, there are some special types of PV panel installed in some locations. For example, in the headquarters of EMSD, the Electrical and Mechanical Service Department, you can see this type of concentrated PV panel, where there's a concave mirror that reflects the sunlight to a particular focal point. And in this focal point, there is a fiber optic guide that will redirect this sunlight to the silicon, so that more sunlight can be focused on these silicons. And in other words, a smaller piece of silicons can harvest more solar energy. So this is the picture that we taken in the visit to EMSD in the last year. So the idea is that we reflect the sunlight. Every mirror will reflect to a focal point, and in this receiver we install the silicon here. These silicons will then convert the solar energy into electric energy at a much higher power. And this is different types of concentrated power PV. We may use either a glass lens to reflect the sunlight to a focal point, and we install the solar cells here. Or we may also use different types of concentrator. In this diagram, this is a line concentrator. So this is a cylinder curve. So the light wave will reflect on this line, and we can install the receiver along this line. It could be an array of PV cell, or it could be a tube, an oil or steam tube, that the temperature inside this tube can be above the boiling point, so that we can collect steam and run in a turbine. Or it could be a point concentrator, where all the mirrors will reflect to the same point, and we install the receiver at that point so that it can maximize the efficiency of energy conversion. You can go to this website to see real installations. And in these installations, both photothermal system and photovoltaic system will be installed together. So there are water pipes running through this cell. This is for the solar thermal system, and also you can see the PV cell. The silicon cells are also installed in the middle. So this can maximize the efficiency by harvesting both solar energy into electricity, but at the same time also capture the remaining heat in the solar energy, which cannot be utilized in electric energy and turn into hot water. Now the pros and cons of concentrated PV is as follows. The advantages is that we can make use of a very small piece of solar panel to harvest a larger area of sunlight, because most of the sunlight will be reflected by this larger area to this smaller area of PV cell. But the installations is more difficult and it involves a larger area, and also it requires a line of sight from the PV panels to the sun directly, so that the reflected beam will always focus on the PV cell, and this requires a tracking system. So we need to check the panel directly through to the sun, and we need to install motors and also the solar sensor, and these motors has to move continuously facing the sun, make sure that maximum area of sunlight can be received on this concentrated PV. And in Hong Kong, because of typhoon and sometimes the insulation is not good enough, and we need a very strong insulation base and also a heavy duty motor to mobilize this PV panel. Now let's look into the electricity characteristics of a PV panel. Now if we have a PV panel here, the sun shines on the PV panel and generate current, and then we have some resistor system along here. And let me ask you a question. What will be the relationship between the current from the PV panel and the voltage across it? So can you guess what will be the shape of this curve? Okay, let me give you 3 seconds to guess. 1, 2, 3. Time's up. In the past, when I asked this question in class and asked students to draw this diagram, many of them will draw a line like this, because they know that the higher the current, the higher the voltage, and this is what we call the Ohm's law. However, in solar energy, it's not the case. The relationship between the current and the voltage looks like this. The x-axis is the voltage and the y-axis is the current. So there is a short circuit current when you short the circuits between the two terminals of the solar panel, and it will give out a maximum current output, which is the short circuit current. And when we open the circuit, we do not connect any component on this solar panel. This is what we call the open circuit voltage. So it will float at certain voltage. And this point is called the maximum power point output, where the product of voltage and current is the maximum. The product of these two values, I multiplied by V, current multiplied by voltage, means power, which is the area under this curve. So remember, the solar panel is not a voltage source, it's a current source. It generates current output rather than a battery which generates a voltage output. So under different light intensity, so the current output will be higher. And there are 3 factors that affect the power output. And the conversion efficiency is not constant. It depends on these 3 factors. First is the amount of the solar energy distributions that can be received from the sun. And another factor is the surface temperature of the PV cell. As a rule of thumb, when the temperature of the PV cell or any semiconductor is higher, then the silicon atom in this semiconductor will vibrate, will move faster, and become the obstacle of the electron to pass through them. So the electron will pass through at a slower speed when the temperature of this silicon is higher. Then the efficiency and also the power of the silicons will be lower. And that's why when a supercomputer and we want to improve the performance, improve the power and current of the semiconductor, we need to keep it in a lower temperature. Another factor is the maximum power point checking, whether or not we can check to the maximum power point, this maximum power point, this point. If the configurations of the PV cells and the electric circuits cannot achieve this maximum power point, then it cannot fully utilize the power that can be generated by the PV panel. What if the power point setting is somewhere here? Yes, you can achieve a higher voltage, a little bit higher compared with this 17 volt to 20 volt, but the current is lower, drop almost half, then the total power output is also much lower. The overall system efficiency is more complicated. You cannot simply consider one factor. You have to consider all these factors collectively. And this diagram shows the relationship between the solar radiations, the temperature, and also the efficiency under different wavelengths of the solar radiations. The blue light, red light, and green light. Okay, so you can see that when the radiations is stronger, then the efficiency is much higher. And also, when the temperature increase, you can see here, the efficiency drop. And the efficiency for blue light is lowest, and then red light is better, and so on.